Today we'll talk about autoregressive models, and this is continuing on our journey towards deep generative models. We've already seen a few RBMs, and not few, two actually, RBMs and variational autoencoders. Today we'll look at one more family of deep generative models known as autoregressive models, and in particular we'll look at two architectures, NADE and MADE. I'll tell you what they mean. They're not just made up terms. And so let's start with the first one, which is neural autoregressive density estimator. Okay, so let's look at each of these terms. I hope the first term is obvious to everyone by now, I guess. Density estimator, what does that mean? Probability density, good, not physics. Okay, so this just means that we want a neural model for estimating probability densities. Okay, and what does autoregressive mean? Of course you don't know, right? If you knew all these, then why am I here? So we'll look at that and see what autoregressive means, right? So far we have seen a few latent variable models like RBMs and variational autoencoders. And these models make certain independence assumptions by relying on the latent variables. So for example, both in the case of RBMs and VAEs, we made some assumptions. In the case of RBMs, we said that given the latent variables, the visible variables are independent of each other. So once you bring in this latent variables, and the idea is that the number of latent variables is actually much smaller than your total visible variables, and you get rid of the dependencies between the visible variables by just assuming that given the latent variables, all of these are independent. So that largely simplifies your factorization and reduces the number of parameters in your model. And in fact, even though it was not so obvious in the case of variational autoencoders, we made a similar assumption there also. We very smartly said that P of x given z actually comes from a normal distribution whose covariance matrix is identity. That's the same as saying that given the z, the x's are independent of each other, right? Hence the sigma is equal to I, right? So we brought in these latent variable models, and they helped us in our eventual goal, which was towards having a tractable model. Of course, even then there were issues. It's not that just bringing in the latent variable model solved everything. Despite having latent variables, we still had to do this expensive MCMC sampling in the case of RBMs. And even in the case of VAs, we had to get rid of this integral or summation or expectation by resolving to this variational inference, right, which tries to maximize the lower bound instead of actually working with the original objective function, right? So just having latent variables is not enough. On top of that also, we had to do certain things. Now we look at autoregressive models which do not contain any latent variables. Okay, the aim of course remains the same, that we are still given a bunch of variables x, right? So this is x1 to xn, and in our example this has been x1 to x1024 because you have 32 cross 32 images, and you want to learn a joint distribution of that. And as usual, for ease of illustration, we'll just assume that this x belongs, all these x's are binary, right? So your x comes from 0, 1 raised to n instead of r raised to n. Okay, that's easier for us to illustrate it. Now, AR models actually do something very bold. They assume that there are no independence assumptions. That's a very convoluted way of saying that. So they assume no independences. So what they assume instead is the natural factorization, and that's not an assumption. They just break down this probability distribution using the chain rule. And we saw the original chain rule had this x1, probability of x1 into x2 given x1 into x3 given x1, x2, and so on. So in general, one of the factors in this factorization is probability of xi given x1 to x minus 1, right? And how would you represent that as a graphical model? What are the nodes in your graphical model? x1 to xn. What are the edges? For xi, what are the edges? It is connected to everything from x1 to xi minus 1, and it connects to everything that comes after it, right? So it's a parent of everything that comes after it and a child of everything that comes before it, right? That's what this figure is trying to illustrate. Okay, so every node depends on all its previous nodes, and all the subsequent nodes are dependent on this node. That's very simple, right? That's very straightforward. Just convert this factorization into a graphical model. Okay, but this is like really frustrating, right? We had this entire saga of 3 weeks where we said that we cannot work with this joint factorization because it has an exponential number of parameters. And after doing all that epic saga, I'm back to the basic factorization and saying that autoregressive models work with that, right? So this is really expensive. In fact, the total number of parameters that you have in this factorization is order 2 raised to n, because some of the factors have a large number of parameters, right? So everyone gets that. So this have the first factor has 1 parameter, the second has 2, 4, and so on, right? So it's a exponential number of factors that you get. So what's this? I mean, I started with saying that this is bad, this is bad, this is bad. We did a lot of stuff along the way to explicitly avoid this kind of factorization, and now we are back to this. So how does this make sense? So this is infeasible, but the way autoregressive models work around this is that they use a neural network to parameterize these factors and then learn the parameters of this neural network. Again, nothing new. What does this sentence actually say? It is giving you the dash for learning a joint distribution. The standard recipe, right? This was the recipe that we discussed, that if you want to learn a joint distribution, you can say that there are certain parameters associated with the distribution. The parameters in turn can be functions of some other parameters, and then you learn those parameters. And that's exactly what this sentence is saying in short, right? So again, that does not really explain how we are going to get rid of this exponential number of parameters. So let us see what this exactly means and how it allows us to bypass this problem, okay? So in terms of neural network, right? So for the time being, just ignore this part. Actually, we can remove this from this slide, right? So what do I want? I want a neural network where I have n outputs, okay? Each of these outputs predicts one of the conditional probability distributions that I'm interested in, okay? There are n conditional probability distributions in my factorization. I'll have a neural network which has n outputs. Each of these outputs will predict p of xi given x1 to xi minus 1, okay? Without telling you anything else, can you tell me what is the function that you'll use for each of these output nodes, right? So remember, we used to do this, right? What's the function for input? It was sigmoid, tan h, and so on. Then what's the output function? Then what's the loss function, right? So I'm just bringing that back. Without me telling you anything else, I'm just telling you that the job of the neural network is to predict these conditional probability distributions, and further, we are assuming that all these variables are binary, okay? So now can you tell me what is the output function that you will use for the output layer? What do you expect the first node to predict? A value between 0 and 1. The second node? So softmax. We need a probability distribution, right? So we should have a softmax. Why not? These nodes are all independent of each other. These are all separate factors. Their sum need not be 1. So we don't need a softmax layer. What do we need? We need n sigmoid functions. Each of these sigmoid functions will predict a value between 0 to 1, which will tell us what's the probability of xi taking on the value 1 given x1 to xi minus 1. So is the output layer clear to everyone? Is that fine? Please raise your hands if it is clear. Okay. So you shall understand why we don't need a softmax function and why we'll have n independent sigmoid functions. Okay, fine. Now at the input, again you are given these x1 to xn, right? So this is the pixels that are given to you. And what you want to predict is probability of xi given xi minus 1, okay? But the catch is that the nth output should see only inputs from 1 to n minus 1. Why is it so? I am saying that the nth output or the ith output should only see inputs from 1 to I minus 1. Why is it so? Because that's the given part, right? The ith output is predicting p of xi given x1 to xi minus 1. So given means what was the input given to me? So the input was only x1 to xi minus 1. So when I am predicting this probability, I should only be looking at the inputs x1 to xi minus 1. Does that make sense? In particular, see, if I give you xi also, then what's the point of predicting what is p of xi, right? I've already seen that. What am I trying to predict? Does that make sense, right? So the given part tells you what is the input given for this computation. So you should only be looking at x1 to xi minus 1, okay? Now if I were to use a fully connected neural network, that means I start with the input layer, I have some hidden layers, and then I go to the output layer. Will that be okay? I'm saying if I had a fully connected layer, I start with the input layer, Think of the multi-layer perceptron that we did, right? So we have the input layer, we have a bunch of hidden layers, and then the output layer, and everything is fully connected. Will that be okay for this solution? Yes or no? Everyone? Why? Yes. So by definition, it's fully connected. So every guy in the hidden layer sees all the inputs, which in turn means every guy in the next hidden layer has seen all the inputs, and you can argue this up to the output layer. Every guy in the output layer has seen all the inputs. And that's exactly the problem that I want to avoid. I don't want every guy in the output to see all the inputs. I just want it to see the relevant inputs. Okay? So that's why a fully connected network does not work. So this neural autoregressive density estimator has a simple solution for this. For every output unit, we compute a hidden representation using only the relevant inputs. Okay, so let's look at X3. This is the output unit that I am interested in. So I will want to first compute a hidden representation. Okay, I'll have a matrix W. So think of this W as the fully connected matrix. Okay, but out of those entire W, I'm going to only look at the first less than k columns. Okay, and from the input, I'm also going to look at only the first less than k columns. Does that make sense? Okay, so that means, what does that mean? My hk only depends on x1 to xk minus 1. So I have ensured that the hidden representation which I am computing has only seen a selected number of inputs, and in particular only those inputs which I was allowed to see. Because this is a kth output, I should have seen only inputs up to k minus 1. Does this computation make sense to you? Right? It does. I'm just looking at the first k entries of the input. Okay? Fine. And now we can compute the output. So I'm interested in the kth output, which actually gives me the probability of xk given x1 to k minus 1. And I'm going to compute it as a function of hk, which in turn is only a function of x1 to xk minus 1. So everything kosher up to this point. I have not seen anything that I was not supposed to see. And vk and ck are just parameters, so that doesn't matter. Right? So if I do this kind of a computation, so what I'm doing in effect is, for every output, I'm first computing a hidden representation which looks only at the relevant inputs. Right? And once I make sure of that, whatever I do with the hidden representation is going to be all fine. Because the hidden representation has seen only the relevant inputs, hence the output computed using this hidden representation will only see the relevant inputs. Is that fine with everyone? How many of you are clear with this? Please raise your hands. Up and high. Okay, good. So now let us look at this equation carefully. So you have hk is equal to first k columns of the W matrix multiplied by the first k entries of the X vector, and then you have this prediction. Okay. How many parameters does this model have? Notice something, there is no suffix associated with W and B, which means they are shared across all the outputs. But there is a subscript associated with Vk and Ck. Okay? And I've asked you the question, what's the number of parameters? So I also need to tell you something about the input and the output. So we'll assume that x belongs to 0, 1 raised to n. That means x is n dimensional, right? It does not matter whether it's 0, 1 or what, but it's n dimensional. And I'll assume that h belongs to R d. So it's a d-dimensional vector. Okay. Now you need to tell me how many parameters does this model have. So start counting. And why am I asking you this question? What will I have to prove to you? That this does not have exponential number of parameters. I have somehow got rid of exponential number of parameters, right? So how many parameters does this model have? What is the size of W? D cross n. What's the size of B? D. Everyone please. This is the second last lecture of the course. I expect you to do this. How many parameters does W have? Everyone should answer. Everyone. N cross D. How many parameters does B have? D. Okay, so you have D cross n and D cross 1. Okay, and the same W and B are used for all the outputs. Okay. How many parameters does the output layer have? What's the size of VK? What's the size of VK? Everyone please. How many of you get that it's 1 cross D? Please raise your hands up and high. Okay. How many such V's do you have? N. What's the size of CK? Oh God, I goofed up. Okay, it's 1, sorry. Yeah, so what's the total number of parameters here? N into D plus 1. Okay, so that's the number of parameters that you have in the output layer. Is there any other parameter obvious from the figure? How do you compute H2? How do you compute H2? You take the first column of W. The reason I am asking you this question is because next time I am going to ask you how do you compute H1. So how do you compute H2 is clear to you. How do you compute H1? Does this start H1 remind you of anything else that you have seen before? Where have you seen such a similar thing? RNNs and LSTMs. You had this H0 state. What did we do with the H0 state? We made it a parameter, right? So similarly, H1 is going to be a parameter here. What's the size of H1? D. So what's the total number of parameters that you have? I think I've goofed up here. Yeah, so you can, so okay, let's just do it, right? So we have n plus 1 into D here. Okay, so n plus 1 into D in the input layer. Then what was the next thing? Okay, so let's just call it ND plus D. And the next one was ND plus N, and then another D. Right? So this is what you had in the input layer, this is what you had in the output layer, and this is your H1. Okay? So in effect, how many parameters do you have? 2ND plus 2D plus N, right? So it's order N. So do you have an exponential number of parameters? No. So how did this happen? We started with a factorization, which is an explicit factorization, and we have been arguing since the beginning of this section that such a factorization will have an exponential number of parameters. So why don't you have an exponential number of parameters here? We shared the parameters, right? That's one reason why I don't have exponential number of parameters. Okay. So now let's just do one more thing, right, before we move on. So I just want to make sure that all of you are clear with this computation. So I had this W less than K into X less than K plus B. Okay. So let's actually see what that means. So what's the size of this output going to be? This belongs to what? RD. Okay, fine. So now when you're doing, say, let's just, so this is X1, X2, X3. Okay, and then you have this W11, W12, W13. Okay, now I said that you just take the first K columns, right? So this would be, if K is equal to 2, then you will take the first column and you will also take the first row from here. What will this multiplication give you? A scalar, a vector, a tensor? A vector, right? So that's exactly what is happening here. But the right way to implement this is actually the following, that you take your input and you mask it. Okay? Then whatever vector you get, which is essentially going to be x1, 0, 0. So then you can directly do this matrix vector multiplication, and that's the same as this operation. But that's the more neater way of doing it. Take your input, mask it, and then multiply by your weight matrix. How many of you get this? Okay. So that's what W less than K into X less than K means. So just get familiar with this concept of masking. We'll be using it soon again. Okay. Fine. How will you train this network? How will you train this network? Second last lecture of the course. You know, I mean, don't pretend. You just know one algorithm that you can use for training. I mean, don't think as if you have 100 algorithms from which you can choose, right? There's only one algorithm that you know. What is that? Backpropagation. Well, after all, this is a neural network, right? What else are you going to use to train a neural network? So if I say backpropagation, what do I need to define? Loss function. What's the loss function? What are you trying to predict? Probability distribution. So what's the loss function going to be? Cross entropy. Sum of cross entropies. Third option is cross entropy of sums. What is the loss function going to be? Now I don't have the problem with the answer. I have a problem with the confidence associated with the answer. What's the loss function going to be? Still I have a problem with the confidence associated with the answer. Only one confident guy. It's going to be sum of the cross entropies. Why hesitate? So let's look at one of these guys. Okay. Now just you need to understand how everything falls in place. So what is your training instance? It's x1 to xn given to you. Okay. That means you know the true probability distribution that you need to predict at x3. Suppose x3 is equal to 1 at the input. Okay. What's the, you said cross entropy. So for cross entropy, you need the true distribution and the predicted distribution. All I'm asking you is what's the true distribution? If x3 is equal to 1, then what's your true distribution? What kind of a random variable is x3? A binary random variable. If I ask you the distribution of a binary random variable, what do you need to give me? How many values do you need to give me? 2. Probability of it taking on the value 1, it taking on the value 0. I am telling you that it was 1. So what's the true probability distribution? 0, 1. The same as the true labels, right? We have seen this a million times. Is that fine? And what's the predicted probability distribution? It's whatever you get here, right? So here you're going to predict some probability and 1 minus that probability, right? So let's say it's 0.7 and 0.3. Now what's the loss function going to be? Cross entropy between P and Q. How many such loss functions will you have? This is the one associated with this prediction. How many such loss functions do you have? N of those. So your total loss function is going to be sum of these n loss functions. Is that clear? Was it so hard? See, at this point I expect you to come up with these answers. I mean, it's like very straightforward, and it's not satisfying if at this point you need me to answer these questions. Okay, so that's exactly what's written on this slide. So the loss function is well defined. We know how to deal with the cross entropy loss function. We know backpropagation. The only catch here is that during backpropagation, the gradients should flow only through those connections which were active. This is similar to something that you have seen in louder? Someone is saying LSTMs? Something similar to what you have seen in dropouts, right? So in dropouts also you remove some connections and then you just make sure that the gradients flow through those connections. And in practice, or while implementing, the way you will achieve this is you will always define this mask matrix. So during forward propagation also the mask would be active, and during backward propagation also the mask would be active. Is that clear? Okay. So you just need to make sure that the gradients only flow along these two paths and not to any of these other guys. Okay. Is that fine? Okay. Now let's ask a few questions about this model. So whenever we are talking about generative models, what are the two things that we have been interested in? Everyone? Abstraction and generation. So let's ask the first question. Can this model do abstraction? That is, once the model is trained, I have learned W, B, all the VKs and all the CKs, and I know I can do that because this is a neural network. I have defined the loss function, I can do backpropagation. Once I do that, if I give it a new X, can I ask it to compute a hidden representation? What's the hidden representation of X? In each forward pass, how many hidden representations does this network compute? In each forward pass, how many hidden representations does it compute? N, right? H0 to Hn minus 1 or H1 to Hn, whichever way you want to look at it. So given an X, you are computing N hidden representations. Now I am asking you, give me a hidden representation. Which one will you give me? This is where you have to start bringing everything together, right? So the idea of hidden representations, the first time we looked at it was in the context of autoencoders. Okay. The idea always behind a hidden representation is that it should capture the semantics of the input. Okay. Now which of these N hidden representations that you have computed captures the semantic of the input? Semantics of the input, the way we have semantics is of course very vague, we have never defined it, but at least in terms of autoencoder you know what we meant, right? Given that hidden representation, we could reconstruct the output. So which of these N hidden representations is the abstract representation of your input? The last one, the first one, all of them, none of them? Last one. What is the last representation actually capturing? What is the job of the last representation? Given H1 to Hn minus 1, reconstruct, sorry, given x1 to xn minus 1, reconstruct xn. Is that good enough for you? What did the hidden representation in an autoencoder do? Reconstruct x1 to xn. Each of these hidden representations that you see here is only capable of constructing one of the inputs. Is that good enough? No. So these models are not latent variable models. By design, they are not meant for abstraction. Right? You can of course come up with arbitrary things that you could take a concatenation of all these and these are, but that's going to be a very large vector, n into d. Or you could take a sum of these or an average of these and so on. But the fact is that these are not latent variable models. They do compute some hidden representation, but by design they are not meant for abstraction. Okay, you could come up with ways of constructing hidden representations from this H1 to Hn, but that's not very natural in the sense of how we did it in the case of autoencoders, how we did it in the case of RBMs, and how we did it in the case of VAs. Does that distinction make sense? Everyone raise your hands if it makes sense. Okay, right? So that's why these are not latent variable models and they are not designed for abstraction. What's the second question I'm going to ask? Can we do generation? What does it mean to do generation? No, I just want to generate samples. How will you do generation? So you're saying you have n independent binary random variables, you could just sample independently from them. So why do you need training and all that? Compute the probabilities. Give me a procedure to sample from this distribution. I have actually given you an explicit distribution, right? Given, okay, before I talk about sampling, if I give you an x, right? So I had asked you to train this on MNIST digits, and at test time I give you a new image. And I ask you to compute P of x. Can you compute it? Can you compute P of x, where x is a vector actually, or a matrix, right? It's an image. Can you compute the probability of x using this model? Yes, no? Everyone? How? You will compute all the, n outputs. These are factors in your joint distribution. You just take the product of them and that gives you the total probability, the probability of the entire thing. Is that fine? How many of you get that? Okay. Okay, that was just a separate question. Now my other question is that how do you sample from this distribution? How do you generate a new image? First question, can you generate the entire image at one go? Yes, no? No. What's the generative process going to be? Think in terms of graphical models. First, find x1. Given x1, find Given x1 and x2, okay, now tell me how will you do it? Not randomly initialized. H1 was a parameter of the model. It's trained. Sample from Px1. But how do you compute Px1? H1 is, remember x1 only takes h1 as the input. And what was h1? A dash of the model, a parameter of the model. That means we have done training, right? I'm assuming that the training is done. So what's the first thing I'm going to do? I'm going to compute the probability of x1 equal to 1 using this formula. Is everything here known? V1 is a parameter, H1 is a parameter, C1 is a parameter. Okay, I have computed this probability. Now what do I do? Sample from? What does that mean? How will you sample? What kind of a distribution is this? Poisson distribution, Dirichlet distribution, beta distribution, normal distribution, everyone? Bernoulli distribution. How do you sample from a Bernoulli distribution? This will give you a value, right? Say that value is 0.4. I'll ask this a million times, I'll ask this another million times if it's required. How will you sample from this? You will sample from a uniform distribution, you'll get a value between 0 to 1. If the value is less than 0.4, you will set it to 1, else to 0. So now you have x1 generated, you have the first pixel generated. Now what will you do? You will set x1 to that value. And what will you do next? Now you can compute h2 using x1. You have a value of x1, you have sampled it. Once you have x1, you can compute h2 because h2 only depends on x1 and the parameters of the model which you have already learned. So again you will get some value, say 0.6. Again you will sample from this Bernoulli distribution, and what will you get? You will get a value 0 or 1, and that you will put it into x2. You will continue this process one random variable at a time or one pixel at a time and generate the whole image or set the configuration for all the random variables. Does that make sense? Is everyone clear about how you will sample from this distribution? Right? Sample one value at a time. Obviously this is very efficient, inefficient? Inefficient, right? This is going to be very slow. Again, nothing wrong with it. All these models come with their own pros and cons. So this is one disadvantage of this model, right? The sampling is going to be very, very slow. You'll have to do a lot of computations for generating one sample from this distribution. Okay, what's the advantage? You're working with an explicit or exact factorization. You're not making any independence assumptions. Okay, fine. Now, notice that this model requires many, many computations, right? Because every time you have to first compute a hidden representation and then compute this yk, right? Okay, but the good thing is that if I want to compute this for the k plus 1th unit, I can just use whatever I had done for the kth unit and just add one simple thing to it. So it just should be xk plus 1. No, actually. Right? Does that make sense? So I had these three columns here and these three rows here. So the first guy only depends on this product. The second guy is actually a sum of this plus this second product, right? So once I have computed the first guy, I can just reuse that computation, right? This follows from basic linear algebra or matrix multiplication. Everyone gets that, right? How many of you don't get this? How many of you get this? Okay, fine. So you can just go back and look at it. So you can do some of these computations efficiently. It does not take care of the entire problem, but at least something can be done efficiently, okay? Okay, so the things that you need to remember about NADE are that it uses an explicit factorization for the joint probability distribution. Each node in the output layer corresponds to one factor in this explicit representation. It reduces the number of parameters which would otherwise have been exponential by sharing the parameters W and B, right? You have shared the parameters in the neural network. It is not designed for abstraction. It does compute some hidden representations, but it's not clear whether they are the hidden representations that you really want. You could do something on top of that and try to get a hidden representation, but by design it's not meant for abstraction. And generation using the model is going to be very slow because it's going to generate 1 pixel at a time. And it's possible to speed up this computation by using the previously done computation. That's what I showed on the last slide, right? So that's, in a nutshell, neural autoregressive density estimator. What's autoregressive? Neural and density estimator is fine. Autoregressive, it's using the previous prediction to predict the next prediction, right? Regression is fine. Auto comes from the previous guy, right? Is that fine? Okay.